Welcome to ALD Stories, a series chronicling the personal journeys of the people behind atomic layer deposition, untold stories of the technology, and deep dives into the history, development, and future of ALD. I'm your host, Tyler Myers, bringing you this podcast from Benek, the home of ALD. Welcome back to ALD Stories. In episode 27, we had the pleasure to meet up with Dr. Rob Clark from Tokyo Electron at the 2023 ALD ALE conference in Bellevue, Washington. Rob, the self-proclaimed manipulator of matter, is a senior MTS and technology director at TEL, where he leads process and integration of thin film deposition methods. Rob began his journey in the semiconductor industry at Schumacher, making high-K and gate electrode precursors before joining Tokyo Electron America in Albany in 2006. Since then, he has been issued over 100 patents worldwide and continues to develop partnerships and transfer technology from TEL to the most important semiconductor players like TSMC, Intel, and Samsung. In this episode, Rob and I discussed how he first learned ALD on CVD equipment, the early days of high-K ALD process development, and his work in making some of the first hafnium precursors for ALD integration in semicon. We also talk about his time as the only engineer at NanoFab North in Albany, how incredibly advanced semiconductor technology has become, and what the next decade of ALD research might look like. I'd like to thank Rob again for a really fantastic conversation. It's full of great stories and intriguing industry insights, and I can't help but mention that his enthusiasm for technology is super contagious. Well, Rob, thanks so much for joining the ALD Stories podcast. Really happy to have you here. For those that may not know, this is Rob Clark from Tokyo Electron, and we're going to talk about a myriad of things, your time in ALD, your rise to prominence in the ALD Tokyo Electron world.
Yeah, I don't know how prominent. But
yeah, we can talk about some of your accomplishments, and yeah, looking forward to hearing your perspectives on ALD.
Okay, sounds good.
Good. So maybe we can start just from the beginning, the background, how you first found yourself working in ALD, thin film dep, surface science type things.
Yeah, well, I mean, those who know me know that right now I'm working for Tokyo Electron, which you mentioned. I should start by saying, anything I have to say about ALD or my opinions about scientific matters are my own. I'm kind of doing this as sort of a private citizen, not trying to reflect the views of the company I work for. And, nothing I say should be taken to be sort of an official word of TEL. It's, my personal own opinion.
You are the manipulator of matter yourself.
I call myself the manipulator. I put that on LinkedIn a long time ago and people liked it, so I kept it. But yeah, my background, I was actually listening to this morning to the podcast with Sean Barry.
Okay, yeah.
The previous ALD, who's a friend of mine, and it struck me when he was going through his background. I was like, oh, geez, I didn't realize we overlapped as much as we did.
Really?
Yeah.
Okay.
Cool. So, by training, I'm a synthetic, inorganic, organometallic chemist, much like him. I went to, Virginia Tech for my bachelor's and master's. I did iridium chemistry for my master's degree, and then moved to UC Irvine for my PhD. And I did synthetic lanthanide chemistry there, working for Bill Evans. And, so when I finished my PhD, I was a pretty good synthetic chemist for, especially air sensitive stuff, metal organic complexes. Right. Yeah. So a lot of time in the glove box, made, chemicals that made some things that, on the Schlenk line that, if they were exposed to air, I was literally making this dipotassium cyclooctatetranide, which was like a precursor to some of the complexes I was making. It was one of my reactants. And you had to make it. If that stuff hit air, it exploded. So it was like,
better be good at air sensitive stuff.
Right. If you had to be good at it and know it, pay attention to what you were doing. Because if you were walking with a glass flask, of course, of that, and air went in while you're carrying it, it would be a bad scene, right? So when I came out, I was basically just a synthetic guy, and I got a job at Schumacher. This is 2000, year 2000. So right after the Y2K bug that was supposed to destroy the internet.
Sure. Yeah, the world was ending. I remember as a kid.
Right. Turned out to be a fizzle. And there, so I got hired basically in June. I started work, I think June, July of year 2000 at the Schumacher unit of Air Products and Chemicals, which was down in Carlsbad, California, North San Diego, right? And they said, we want you to come make precursors for CVD processes.
Sure.
So basically they were talking about, most people were talking about chemical vapor deposition. Of course, ALD was known.
Mm-hmm. Not too big yet.
But we were CVD precursors for the semiconductor industry. And, they sold a lot of things like TIOS and Trans-LC, which is transdichloroethylene. So silicon oxide precursors, yada, yada, yada. My job was high K and metal gate precursors. So I came in, there had been a chemist ahead of me that was named Yoshi Senzaki, who's now, I think, a jazz musician. But he went on to pivot. He went into the equipment industry for a while and was pretty well known in the industry. And so he left, and they hired basically two new chemists, myself and a guy named Sinjin Lee, who's still at Versum, which is what that became Versum eventually. And I came in, they said, okay, we need, high K. In 2000, it still wasn't, 2000 was right about the time that people started getting to the point where, they're making transistors with different high K dielectrics. Mm-hmm. They're trying to figure out what high K dielectrics will work in the transistor, right sort of thing.
At that point, nobody has high K in process.
Right. People were trying, aluminum oxide, tantalum oxide, any kind of high K oxide they were trying, and they were making really terrible transistors because they didn't really know. There was a big learning curve there where you had to figure out, okay, we actually need an SiO2 interface layer. That helps, right? We actually can't, in a lot of the cases, it's either hard or impossible really to grow it directly on silicon without an interface layer anyway. Right. And then you figured out that, we need that interface layer, it's not. And they were trying to figure out, what's the gate that we can work? People were started with polygates, and the device guys took them a while to actually figure out that, hey, we need some kind of metal gate on top of this. We need to go back to using metal gates, which they had used before in the industry. So yeah, that stuff was all going on. And at the same time, we were selling things for CVD. Applied Materials had a CVD high K program going. We were giving precursors to people like Dimly Kwong at UT Austin to do CVD, hafnium oxide, hafnium oxynitride. And then you start hearing about this ALD thing, right? This atomic layer deposition. And of course, it's, the initial view is, well, this is basically a variation of CVD, which it's technically it is kind of a variation of CVD. And then they, of course, had the first ALD conference, which I didn't get to go to, but one of my colleagues did go to it. And he came back and he's like, yeah, this ALD thing, it's real. We got to do something about it. The funny thing, the lab that I worked in, Bill Evans' lab, so he mentioned Randy Broomhall Dillard at the beginning of his podcast. Randy was my lab mate.
Really?
At Irvine.
Bill Evans' group.
Yeah, so he was a couple years ahead of me in Irvine in Bill Evans' group. And he actually, while I was there, he got his postdoc with Roy Gordon and drove across the country to Harvard. He actually hit a cow on the way across the country. but
well, there's enough in the middle.
Yeah. So Sean and I had similar backgrounds. We also have Randy Broomhall Dillard in our past.
Wow.
So he was a good guy. We start hearing about this ALD process. And I had actually, Schumacher Air Products had actually licensed some of Roy Gordon's precursor work, CVD, for tinitride. So they were actually paying royalties on one precursor back to Harvard, based on Roy's patent, right? And so we were at that time. Schumacher was still running. They called it the Schumacher Conference.
Okay, it was just on precursor development.
It was basically like a small little, like a meeting. They would have a one-day meeting. We'd invite different people to come and talk. And they, when I started work, they kind of said, oh, we're going to run this conference, and, could you figure out someone to invite to come out, and, we'll pay their trip out, and a professor somewhere. So I said, well, I don't know him, but I looked up Roy Gordon's phone number on the web, and I was flabbergasted that, I just called his number, and he picks up the phone. It wasn't a secretary or anything.
Early days of the internet,
world famous professor, right? So,
surprised his number was just
it was published in the chemistry. There was like a web page for his group or whatever, and it had his phone number. So I called expecting, I'm going to get a secretary,
right?
And he picks up the phone, and I talked to him, and I told him, who I was and who I worked for, and of course he knew Schumacher, and because he was, he was aware that we were licensing his IP, So he said, oh, I'll be happy to come out and give a talk, So that's how I kind of met him.
Sure.
Right. He came and gave a talk at this Schumacher conference based on my invitation. And then sure enough, when the ALD conference came, we had ASM was coming to the country, and they were basically bringing that microchemistry designed 300 millimeter pulsar that they built, that they had made the learning from the F-120 kind of things that you see in Helsinki, and developed a real 300 millimeter tool to do, high K deposition using hafnium chloride. And they needed precursor suppliers, and that was, that's my gig, right? So we get contacts from them, and you start hearing about the ALD everywhere. You have this new equipment maker that's coming in with this ALD system that Semitech is putting in, and Motorola is putting in, and Intel is looking at, and all these device makers are out there trying to get this system up and running, right? All our customers. And we said, well, we need to figure out how this stuff works. So
at Schumacher,
we had a little applications lab down in the basement run by this guy named Art Hotberg, who was a real character. And he so it actually took a lot of effort to get your precursor tested, because Art is one of those, or was one of those guys that he's incredibly smart, incredibly good at his job, and he doesn't have a lot of patience for anybody that he thinks doesn't know enough, right?
Sure.
So, and
you're going to slow me down.
Right out of coming right out of your PhD, Art kind of looks down his nose at you and goes, oh, you don't know what you're doing. And he was right. When I first got there, I didn't know what a transistor was, really. I mean, I knew what it was, but I didn't. If you'd asked me, draw a transistor on the board and explain how it operates,
right,
I would have gone
step by step. Show me the fat steps.
So I'm on this learning curve, and I want to get my stuff tested. And Art, and he had one guy that was kind of his assistant, and they had like, I don't know, 4 or 5 deposition systems down there, right?
Okay, nice.
And they could only really run, each one of them could only really run one at a time, right? So you have basically 3 systems sitting unused at any one time almost constantly, and you're trying to get your stuff through. So you'd say, hey, when can you test my precursor? And he's like, well, we got to do this one, we got to do that one, we got to do this. It's going to take, a month and a half before we get to your new little thing to test it. And he said, it's not going to work anyway, so don't worry about it. And I said, well,
Did you press him on that?
could I, learn how to use the systems?
Mm-hmm.
And he said, well, yeah, but I don't have time to teach you. And I said, okay. So I just basically went and started hanging out in the applications lab and watching what he was doing and saying, asking him questions. And at first he didn't want it. He was like, yeah, whatever. Yeah. But eventually he finally started saying, okay, this is what you do.
Mm-hmm.
This is how how we work the gases and stuff. And it was all little switches. So one of the best ways to learn process in the world is to have to open all the valves yourself.
Absolutely.
To like sit there and open the valves and turn on this gas, turn on that gas, get everything stabilized at a pressure, and then you bring the precursor in, and turn it back off.
Yeah, I've mentioned this probably before on this podcast, that in the George group, we basically home built all of our systems. And I mean, basically every first year student takes apart, rebuilds, and you need to put it back together, test it, and make sure that it works. If it doesn't, take it apart again. And it is the best exercise that you could possibly do to learn how these operate.
Absolutely. And so for learning like how a deposition system works, it was a good learning experience. So we're doing these CVD things, and then this ALD stuff starts coming up, you start hearing. And we said, okay, we got to figure out how we're going to test ALD precursors, or how we can start working on ALD, right? So, and Roy is, of course, publishing this stuff in that time frame, 2000 to 2006 is when I was there. So Roy starts publishing a bunch of ALD stuff, which he picked up from the guys in Helsinki, and so my boss goes, you should go to Harvard and take a look at how Roy does this ALD stuff, and then come back here and build one of these systems.
Cool.
So Roy was using these little tube furnace systems that he came up with. It's basically a stainless steel tube, and he had a little aluminum boat, which he kept. They had the temperature sensor right embedded in the aluminum, and they're sitting there with the thermocouple, using basically the thermocouple to move the boat in and out. So the thermocouple would go through the end cap, and they would put the boat in there with their little chips of silicon, pieces of wafers in there, and basically it would sit in a tube furnace for heating, and the gases would come in on one end and good vacuum on the other end.
Sure, simple.
Very simple flow system, right? So I went to his lab, and he had like 5 or 6 of these things going at the time, and he showed me, how they hooked the precursors up, how they heated everything. They just wrapped everything in heat tracing. It's very simple. And so I had my notebook there, and I sketched it all out and brought it all back to Carlsbad, and we just copied that system.
Nice.
And that's how we started doing ALD.
Cool.
So that sort of hafnium chloride system starts getting more and more developed. When they first showed up in the US in like 2000, 2001, I think 2001, 2002 kind of time frame, the container was terrible for delivering the hafnium chloride. It had a problem, like one system, they opened up the vacuum oven and everything was rusted inside because the HCl was coming in and mixing with moisture and started corroding everything. But they year later, containers getting better, right? Another year later, new container that has, we had a fin container, there was a tray container out there, and so people started solving, like, how do you deliver this solid precursor, right? How do you handle the vacuum systems? They had to, they probably had, you could probably talk to Eric Shiro, and he could tell you all the nuts and bolts of what they had, all the different stuff that they had to fix on that.
So when you're at Schumacher during this time, what pieces of this process development are you working on? Are you just
so
doing
we were
precursor
mainly
development
working on we were working on getting the purity of the hafnium chloride right. There were questions, once people settled on hafnium, right, there was questions about, like, there's, say, somewhere from 500 to 2,000 or 2,500 ppm of zirconium in most hafnium chloride. Just as a result, zircon, the ore for zirconium and hafnium, the Cotton and Wilkinson chemistry book, if you open up Advanced Inorganic Chemistry, which is like the Bible of inorganic chemistry, right? They say it's the two most similar elements in the periodic table are zirconium and hafnium. So they're really hard to separate, right? It's not quite separating isotopes because there's a big mass difference. Right. But from the standpoint of reactivity and even kind of vapor pressure, they're really close together. So it's really hard to get low zirconium hafnium.
Sure,
right?
Gotcha.
So, we were working on things like that, like how do we purify this stuff? How do we get the metals down? How do we get enough batches together that we can actually get some statistics for process control, for lot-to-lot variability and things like that? And how do we, the container as well, how do you deliver this stuff properly? Right? So we had a container that we came up with, was used in manufacturing. And so all of those issues. And at the same time that this is going on in the logic end, the DRAM guys decided, hey, we need high K. Which, like, Perik Banerjee was working at Micron, who you talked to as well. And so they wanted high K as well. And they actually beat the logic guys to production with the ALD high K.
No kidding. That's right. Yeah.
Using different precursors.
I know. Everybody talks about Intel 2007
right.
high K.
Yeah. But it was actually, Samsung was running high K in their DRAM before Intel was running high K metal gate. And it was because it was just so much easier to solve the issues with the capacitor than it is with the issue on the issues with. Plus, they were able to, benefit from the learning that the logic guys had. So they went right to hafnium oxide and said, okay, this one looks like it'll work. Maybe it'll work for us. Right. They went right to it.
Steps.
Right. And they used different precursors. So in logic, it became the chloride was mostly used for the ALD process. The amides were mostly used on the DRAM side because they needed the higher aspect ratios. The chloride's not really good for that. So
you're at TL in Albany now. Can you explain that ecosystem that was there? Because there was like TL working with IBM, and the nanotech campus is there also, if I remember correctly. Was that all kind of like working together? Yeah, so there was this, they started, they came up with this idea of having this sort of industrial academic research center, combined research center. And IBM was really the big industrial driver for wanting to do that in Albany, right? They had Yorktown, they had Fishkill, they had a fab in Fishkill. Of course, they're headquartered in New York, so they could get some government money to help set this thing up, and they could see the idea. They bought into the idea that was pitched from the university, like, hey, let's do this Albany nanotech thing, and let's put a fab
in Albany on the SUNY campus, and you guys can bring tools in there and do research, and you can work together with other companies on site and do research together. And somehow between the management of IBM and TEL, TEL agreed that they would be a partner in this. And I think TEL was the first other company to sign up for it, other than IBM. And so IBM basically convinced TEL, from what I understand, that, this is a good idea. You can come here and work with us. We can work together. We can do joint development projects together. You can put your equipment in. We'll provide the device knowledge and work with you to develop these processes. And it's a good model. It's there's a lot of good work that goes on in that facility. It has a full tool set that allows you can make CMOS in this facility. You could really do it from front end to back end, like IBM's big 2 nanometer paper that they did 2 years ago, I don't know, something like that. That was all done in Albany.
No kidding.
Yeah.
It's really interesting for me. I told you this when we first talked. I grew up not very far from Albany, and it's interesting that this was kind of all happening under my nose, and I didn't really know what was going on.
Right.
The only time I did go visit the nanotech campus once as a kid. Then I don't remember what year this was, but Global Foundries started in Malta around, maybe I was a teenager. They had people.
Yeah, I think it was like 2008, something like that.
Yeah, that sounds about right.
We're going in there.
Was there some shift in the industry when that happened? Was it, did that affect things that were happening at TEL and IBM?
Well, there were big shifts going on in the industry all through that time, So, in 2006, when I went there, I went to the Fishkill fab. We had tools in Fishkill that IBM was using. And that was my first experience, actually gowning up and going into a real 300 millimeter manufacturing fab, and that was like the first fab that had the track systems overhead where the wafers were running around on the tracks, and it would come and drop the FOUP down onto the front end of the tool and sort of automatically load the wafers and get them running, all controlled by computer. It was so the operators didn't have to go move the FOUPs by hand around the different tools.
It must have been so cool.
It was pretty wild to step into that, and like 2006 to go look there, and you're like, what? Well, the wafers are running around up here, and then you see this thing drop it down on cables, and it just lands on the tool and goes in and starts processing.
The Steven Spielberg design,
right? Without anybody interfere, nobody. I had gone from I need to flip every switch to now you can drop down this FOUP and you don't even have to hit start.
And that's in the span of like 5-6 years.
Yeah. And when I got to Albany, I went in. They had so Albany has a lot of clean rooms. So they had what they call NanoFab South was the first one, and then they had what they call NanoFab South Annex, which was a warehouse that got converted into a clean room, and then they had just before I joined TEL TTCA in Albany, TEL Technology Center America, they had they built NanoFab North, which has now been expanded with this NanoFab Center. So they've been expanded that since then. But right then they built that, and I showed up, and basically the tool I was supposed to work on was really the first deposition tool in that whole fab. So there was a wet cleaning tool in that fab. There was like a few metrology tools installed right away. And my deposition system was I think the first one or one of them, the tool I was going to work on. So I could go, and we had, a good budget for wafers and everything. I could go and run 25 wafers. I came from, load the wafer yourself, run it, and I could, at Schumacher, I could run, 10 experiments if I stayed in the apps lab most of the day.
Yeah, little coupons things.
Right. Well, mostly 4-inch wafers.
4 inches, okay.
That's what we were using mostly, is 4-inch wafers. And so I went from that to, put a FOUP of 25 300 millimeter wafers on the tool, go in the software and program a different set of process conditions for all 25 wafers, hit start, and walk away, go away for an hour and a half, come back, the wafers are done for you. And since I'm the only deposition system in the fab, I could walk right up to the ellipsometer and put them on the ellipsometer and hit start, So I could build, like if I wanted to do a saturation curve, I could do 5 saturation curves in one FOUP and have it all measured in about, have it deposited and measured in like 3 hours.
And an R&D process engineer's dream.
Right. So, and you can't do that anymore.
No.
So I could, by the end of that, if you said to me, okay, give us your best uniformity process, I had it dialed in to, 10 degrees, something like that. This temperature, these are the pulse times, this is everything, for water and for ozone, for zirconium and for hafnium, all of that was, I could do in like 6 months. I had characterized both of those processes about as fully as you can do it.
So things make sense now, because if I remember right, you were patenting and publishing a lot during those like early years.
Yeah, well, we did. Like I said, we were working with IBM, and they were publishing too. They wanted to go to the conferences and publish, so it made sense from both sides that hey, you guys do the process, we'll do the device. We can make it work together that way.
So these early years in TL, you guys say TEL.
Right.
I don't know why I would say TEL, but yeah, a friend who works at TEL also.
Right.
Yeah. In any case, those early years when you were at TEL, sounds like you were doing pretty much mostly like high K.
Mostly high K. We were also doing metals. We were doing tinitride and things like that for metal gate. But I was mainly focused on the high K oxides, which took a long time to go anywhere for us, because we were focused on the amide system, not the chlorides, which I had worked on previously. So yeah, it was a good way to really learn ALD processing well, and you learn. I think some of the other people you've interviewed have pointed this out. People think about this saturation curve. You've just got this saturation curve, and if a lot of times, if you were dealing with somebody who just had that sort of basic understanding of ALD, their idea of process development was, well, do half a second, 1 second, 1.5 seconds, 2 second pulse time on the precursor, and do that on the co-reactant, same thing, and then we'll pick the right times and we're done.
Yeah, right.
And that's not how it works at all. So
maybe in an R&D lab at a university,
right,
it can work like that. Yeah.
So yeah, I mean, at a high level, you can explain it all that way, but really, the problems you have are things like, how do I deliver the precursor? What are the right inert gas flows that are going to go on in this? What pressure should I be at? What temperature is the right temperature to run this thing at, right? Yeah, and then how do you solve the non-uniformity across the wafer? Because, even though you can run a saturation curve, doesn't mean you're going to have less than 1% standard deviation across the wafer. you can have 3 or 4%, and you sit there scratching your head going, why is it not 1%? It should be 1%, you know?
Yeah, it's easy to get everything to work when you're doing it on a inch
Right.
by inch coupon in your.
Well,
your
a lot of
open
people
flow
that do ALD are working in systems that aren't really doing as much ALD as they think.
Sure.
A lot of them have even a sweet spot where they have to put the little chip.
Yeah, right. This
and if
2 inches.
So if it's an inch off, if it's an inch farther back or an inch in front, the growth rate changes, and that's a sign that you're not 100. You're not really in your ALD regime. So, and a lot of the processes suffer from, thermal decomposition of the precursors, or there's some co-reactant. Water, if you're using it, or ammonia, are both sticky. Right, they stick to the surfaces of the chambers. It can take a long time to purge out. It depends on what you got around the wafer. How big is the volume of your system? What's the flow pattern of your system? Those kind of things. So, we were working at the early days. For me, we were working with what we called counterflow ALD, which we did some publications where we kind of showed it. But it would actually send the precursor from one side across the wafer, and then the oxidant from the other side across the wafer. So
interesting.
It was switching back and forth, right? And going like that. So you were coming. It's kind of interesting because you could get I could in ASM, and their system was a cross flow also. Right. Yep. So in the cross flow systems, you can actually, if you have a high sticking coefficient precursor and you're subsaturated, you can grow the film on half of the wafer, and you'll have this growth front.
Gradients, yeah.
Right, you'll get a big thickness drop off halfway across the wafer. And because mine would come from both sides, I could do that with the oxidant. In the case of ozone, if I used a small enough dose, I could do that with ozone as well, but not with water. With water, it was either all the way or nothing, and then we couldn't control it tightly enough, but I think it's mostly because water is sticky and it hangs around in the chamber and diffuses around in the chamber. So once you got enough dose that it was really getting to the chamber, it was enough to saturate the whole thing.
Right, you
never got this sharp growth front from the water side that you could do. But with ozone, you could do it. So I could actually see, am I undersaturated in oxidant or undersaturated in precursor by just looking at the thickness map on the wafer, because it was coming from two different sides.
That's cool. It's really clever.
Yeah. But it was a really...
So nowadays, you're no longer doing process development. You're more technology director at TEL. What is your relationship with ALD now? How often are you working and thinking about the process? I know you have a myriad of topics that you work in now.
I think that, it's as an equipment guy, right? Or as an industry guy, we are very agnostic about ALD versus CVD versus PVD. What we care about, what we want is whatever gets the job done, right? So for a long time, if you were going to do ALD, they really didn't want an ALD film to be thicker than 10 nanometers.
Sure.
Because it just the throughput was too low,
right.
Or whatever, So ALD was kind of confined to really thinner films and stuff like that. But nowadays, that's even starting to change a little more. At the same time, the feature sizes have continued to shrink to incredible, I was working on a 45 nanometer node way back then, a 32 nanometer node, and now we're talking about 3, so the feature sizes have gone down. The high K thickness is nominally very similar to what it was even when it was first implemented. It might have gone from 20 to 25 angstroms. Now it might be 18, or something like that. but it hasn't gotten much thinner because they couldn't find a way. Nobody found the follow-on that enabled you to scale the EOT more. So high K was like, boom, you scaled the EOT from 11 or 12 angstroms down to 8 to 10 angstroms, and maybe they've gotten it down to 6 to 7, but it hasn't really continued to scale, and that's why you end up with things like FinFET, because you're trying to overcome the short channel effects from not being able to scale the EOT. Right. So, and now we're going to be doing gate all around, which made, the fins made ALD even more necessary. The gate all around is going to make it even more necessary,
What else could you possibly
and we've also got this problem now where, you're trying to fit functional layers inside of critical dimensions that are going to be 10 nanometers, or even sometimes 5 nanometers spaces that you have to get films to go in there. And it's okay that it's a 2 nanometer film and it'll fit. That works.
Not much room for error.
Right, but you don't have any room for error. And you have to get it, it's got to be the same thickness everywhere, all the way across the wafer, So you have all these very stringent requirements for the process. And, on the academic side, they have that old joke, like, once you get the data you need, stop doing experiments because you don't want to prove yourself wrong. For us, it's like, we have to do this 6,000 wafers in a row, and then do a maintenance and then do it again, or 10,000 wafers. And we would run 10,000 wafer marathons, and you have to, every wafer you check, it should be within spec, and that's actually really hard to do, even if you know what you're doing.
Doing 10,000 of anything the exact same way, regardless of semiconductors or a bench press.
Well, and the customers are running 60,000 wafers a month, 80,000 wafers a month, and they'll have 10 of these tools lined up. They all got to run the same. Thousands of wafers in a row. And it's, the really cool thing about the semiconductor industry is, right now, whatever is coming out of TSMC's latest process, at this moment, they're the leader, right? Whatever's coming out of their process is quite literally the most advanced technology that the human species has created.
True. No one has ever put that way to me before.
It's the most advanced manufactured product in the world in history. You've got billions of these little tiny transistors in each chip. And, when you think about it, it's just incredible. It's
true.
It's like building New York City at nanoscale 200 times on the wafer, with a billion buildings in it.
It's hard. I think sometimes, when you're in the technology, and kind of in this industry and in the field, to forget that like what we're doing was pretty unfathomable not that long ago, and to people who are not in the industry, it's completely incomprehensible. Trying to explain these things to people who aren't in semiconductor is really hard.
Now, at least, now since the pandemic, and we had this chip crunch, right? The chip shortage. Everybody woke up to the fact that these things are really important.
Yeah, absolutely.
So it and then there's that book Chip War that came out.
Yes.
Which I think, like if you work in semiconductor industry, go get that book and read it because it gives you the history of how these things, and it also gives a very good view of the geopolitical picture out there in the world, how these things are done. Like you look at to get off the topic of ALD for a second.
No, please.
Look at EUV lithography. That's an amazing process, that these guys have a drop of molten tin falling down, and they hit it with 2 laser pulses in a row in milliseconds apart, and 1 to form it into a pancake and the other one to obliterate it and release the EUV photons. And this is happening, thousands of times in a minute. It's ridiculous.
Yeah, and then directing it all through mirrors,
and then going all through mirrors and getting it to project down onto a chip and lining up one mask with the other mask within, say, 5 nanometers of each other to get.
And then do that 10,000 times.
Right. I mean, you can make your whole career on one kind of tool in the semiconductor industry. And it's the most advanced version of that tool that has ever existed in human evolution, the human history. And like I said, whatever's coming out of TSMC right now is the most advanced thing that we've ever made and manufactured in any way. It's nanotech. I mean, the whole thing is nanotech. So you talk about people talk about like nanotech on the clothes to kill bacteria or stop stains or repel liquids or whatever. But the semiconductor industry it's our old processes that are being used to make things like MEMS and these and solar panels and hard disk heads and all of these things that are just like the old semiconductor stuff. and so it's an exciting field to work in. It's interesting to sit there and work with the people at Intel or the people at TSMC or the people at Samsung, and that they're doing the most advanced stuff in the world, and you're trying to help enable that stuff. It's a great career. And you can see, like, we all knew what the semiconductor industry was about, what Moore's law meant, and what it meant to society and everything. But you could pull out your iPhone and say, without us, this doesn't work, right? But now we're all carrying around what was a supercomputer 30 years ago in our pockets, and we have a connection. We've enabled communications technology that lets me, I can search. I have almost the entire human knowledge, body of human knowledge available to me if I just pull my phone out and go on Google and start searching. I can go to Wikipedia and learn almost anything. You can download scientific papers right at your fingertips. It's from when I was a kid, when we had corded telephones. We could only go so far from we had like a 20-foot cord on our phones, and that was as far as you could get from the wall that had the phone on it. It
was a luxury to be in a different room to.
I mean, there's downsides to it. Now if you call somebody and they don't answer, they know you called.
That's a problem. I'm really bad at answering texts and calls. Sometimes my phone's almost always on silent, and it's like it just it takes away so much attention. Yeah.
But I mean, overall, the benefits to society, and if we're going to solve the world's problem, we're going to solve global warming. We're going to develop you can't sequence a genome without computers.
Right.
There's nothing that pharmaceuticals, healthcare, transportation. There's no product out there in the world right now that really operates without. None of the technology out there in the world is independent of compute.
Yeah, no longer.
Right. It can't, any researcher working in science in the world, if they didn't have a computer, they'd be dead in the water.
That's right.
They could not compete.
I mean, even now, you go to a new job, it won't almost even matter what job it is. You probably are being given a computer at work.
Right, and the beauty of ALD is it enables.
Yeah, makes that
without happen. ALD, we can't make the transistors that make all this happen, right? So we can't make the wiring that makes all this happen.
Nope.
It would all fall apart.
Yeah, this has been a really, really cool conversation. I think maybe we can wrap up with like one last question then, since we're at the ALD conference now,
Right.
recording this. Just curious if there is a talk or a person you're really excited to see again, or something in ALD that you're really looking forward to learning about this week. Something that's got you excited.
Like there's been several talks on the selective deposition. So, I guess like I said, I'm agnostic about ALD versus CVD
Sure.
and all of those things because, like for selective deposition, CVD is arguably better for a lot of processes than ALD is. If you're going to do, of course, from a chemist's perspective, ALD is easier for me to. For a chemist, ALD is like, oh yeah, let's do this, and it does this reaction on the surface, and let's put in this other reactant, and it does this on the surface. And so when you're thinking about the surface chemistry, it seems like the obvious choice for selective deposition. But like looking at how people are developing, small molecule inhibitors, and they're developing their understanding of how to do selective ALD, selective ALE, which is becoming a huge thing. That really, his name was Tristan something, the Intel guy. Tristan Tronic, right? That talk just blew my socks off. It was an amazing talk, for a guy from Intel to come and say, he actually showed some really high value problems to a whole room full of experts, professors, students that are experts in these areas. And he basically created he's probably got 200 people now working on his high value issues out there.
Yeah, here's the next 10 years of research.
Right. He just laid the foundation for the next 10 years of research that'll get us to, transition metal dichalcogenide devices or something. Get us to, what do we do when we're, the industry is going to keep naming the nodes smaller and smaller. Yeah. But it doesn't actually make sense to think about things that are smaller than 3 angstroms.
Right.
So, I mean, once we get to the 3 angstrom node, what do we call it from there?
Are we going to have a Q node?
There's probably marketing people at Intel and TSMC and Samsung that are thinking about that right now. What do we call this? How are we going to name the nodes when we get to the end of the roadmap? But I thought that talk to me was really good because every time he introduced a subject, I was sitting in the audience going, and I know the materials. I know what materials are important in the industry. And normally you don't get a good layout of, one of the things that we haven't been good at is telling the academic guys who do the early development of these. So, like as an industry, we really need to get better at directing the research, the early leading edge research towards directions where it's going to create a high value solution that's going to impact what we do 10 years from now.
Yeah, you don't want the researchers and academics to be guessing that this is going to be impactful. And okay, maybe people have their pet projects, but I think it's a lot of researchers' dreams to, have the technology that they're working on actually make an impact. And if you don't know that this is what looking for.
I think there should be room for people to just go off and do whatever process they want.
Of course.
Right? Like you want to do a process to deposit lithium or titanium or, titanium we use. So titanium's in there in the industry. It's in the devices, right? Those kind of processes are extremely difficult and, but and sometimes it's a solution looking for a problem. And that's okay because you might have a problem later on that comes along where you need that. But at the same time, you have to be aware of what's really going on. Like when we're talking about selective deposition, a lot of people are talking about, well, here's my one growth surface and my one non-growth surface. But when we're actually doing integration, we have 4 or 5 materials there almost all the time.
Right.
So you really need 4 non-growth surfaces and 1 growth surface, or something like that. Or maybe you want 2 growth and 2 non, something. So there's all kinds of variations on that we're just starting to sort of crack the lid on,
And you wrote a review with Greg Parsons on
right.
ASD,
the
right?
ASD review, yeah. Really, Greg wrote the review, and I wrote like one section that's like 15 or 20%. I joked with him that it should be. My joke about it is the author list should be Greg Parsons, Rob Clark, and Greg Parsons. So he should be the first and the last author. And
what does he have to say about that?
Well, he decided he wanted to be the first. He had his pick. It's really, a lot of it is his paper. I did the applications part. Like, how do you use this to make semiconductor stuff? And it's like we're just cracking the lid on that, and that's the first time that we're really breaking out of the mold of the planar process, which has been sort of the top down, put a layer down, pattern it by lithography, use that as a mask to do something, right? And then etch it away, and this is how you build the structure up,
right,
all from the top down using lithography. And now all of a sudden we've got a process where we can take the information that's already on the wafer and use that to direct where the film's going to go. But like I said, that the stuff you see at these conferences, some of it you look at it and you go, oh, that's not that, doesn't matter. But you get these talks like Tristan's talk in the plenary, where it's just like, okay, you just gave us a roadmap for the future, or there's a new way to think about it. Like, at the first time you see somebody doing a small molecule inhibitor or doing a SAM-based selective deposition like Stacy Bent's work, ridiculous, like the impact that her lab has had on the whole industry in terms of thinking about how to do selective deposition and how to, you can literally see like the work in her lab from 10 years ago showed up in a TSMC paper, at IEDM. And it's like, I can draw a direct line from one of her papers to what they were doing. It's amazing when you get these people that are that smart, that creative, working on these processes, and they come up with something new that you never thought was possible.
Well, this is why they're in the lab doing that, and I'm sitting here asking them about it.
Yeah, but I'm always just grateful that, these guys let me play in their sandbox,
We're really lucky for the people that we have around, and
Oh, yeah, absolutely.
I think that's a really nice note for us to end on then, Rob.
Yeah, thank you.
Well, thank you so much for your stories and perspectives and your thoughts on the industry. This was really
It was
cool.
Fun.
Yeah,
Thanks.
I had a lot of fun here. I appreciate
Me too.
taking some hour out of this very busy time that we have. There's a lot of people to talk to and a lot of things to listen to, and as we just discussed, 1,000,001 prolific things that are happening around us.
Yeah, and then thank you for putting this forum together where you can, like yesterday I was listening to Mika Riddle talk. I used to he talked about he was trying to read every ALD paper. I used to have like a stack of Leskill and Riddle papers all the time. And those guys put out so many papers, I couldn't read them, even just their papers, all of them. It was like, but I was just going like, I had like a standing search for these guys, and you're able to come and talk to them and find out like what it was like from their perspective when they were really inventing ALD, working under Santala and starting to commercialize these things and turn it into a technology that the rest of the world relies on now. So
it's information that's not easily accessible. So I'm really fortunate that I have these opportunities to talk to such cool people, including yourself. So
it's been great.
Yeah, thank you again, Rob. Much appreciated.
Yeah, thank you.
All right.
Thanks for listening to ALD Stories with Benek. To stay updated on new episodes each month, please follow us on Spotify, Apple Podcasts, or Google Podcasts. We hope you enjoyed the show. I hope to see you again in the next one.